So this is the term-by-term differentiability theorem that we spoke about in the last video. This is what so basically what it says is that if you know that you have a family of differentiable functions defined in an interval a, and the sum of the derivatives of these fn's converges uniformly to a limit, a limiting function g of x. So uniform convergence is important here, and you also need to you know that derivatives are only defined up to a constant. Functions that agree on whose derivatives agree on a connected set are the same up to a constant. So you need some information also about the function. So if there exists a point in the domain where the sum of the fn's converges, then the series of the fn's converges uniformly to a differentiable function of x, f of x, satisfying that the derivative is the sum of the derivatives term by term. So there are many things here that we need to define first, so that we first have a family of differentiable functions. This is stated on an interval a, but the book, but we actually not, we don't use any generality by stating here. This is for practical purposes. We can think of these functions defined on the interval AB, the closed interval AB, and they're such that the sum from n equals 1 to infinity of fn prime of x converges uniformly to a function g of x. Keep in mind that this is information about the sum of the derivatives, not the sum of the functions. So we know that there's a function, a limiting function g of x, such that this infinite sum here converges to in a uniform fashion. Now we also need a condition, a point. Point x naught in a b such that the sum dfn at x naught converges So this series converges. Then the series sum of n of x, now we are moving the point, converges uniformly to a differentiable function f of x and f prime of x is equal to this g of x that we obtain up here. So we are drawing information about the infinite sum of the fn's based on the convergence of the sum of the derivatives, which we know converges uniformly. I mean, this series converges uniformly to a function g of x. And we also need to know that there's a point such that the series converges to something. It's convergent for that at that particular point x naught. Then combining these two pieces of information, then we can conclude that the series converges uniformly to the differentiable function f of x. Not only does it converge, but the function it converges to is differentiable, and f prime of x is equal to g of x. And this has some applications. The most important ones. This is what I said. It was going to be the most. I mean, this is going to be the end of this section for us. Is what we. I mean, this most important applications are when we know. When we apply this to power series, when the fn of x are equal to just say x to the n. These are power series, right? So this is what we have in mind. I mean, this is what we want to apply this to. And a couple of theorems that we need to know. This is theorem 6.5.5. If a power series converges pointwise on the set A, subset of R, then it converges uniformly on any compact subset of A. Subset, if you want to give it a name, K, subset K of A. So what is the example here we have in mind? So example, the harmonic series is the geometric series, I'm sorry, x to the I from I equals 0 to infinity. This actually, well, this converges to, this is actually equal to, it converges to 1 over 1 minus x for x in minus 1, comma 1. Well, this convergence here is pointwise. So according to the theorem, theorem 6.5.5, this sum, this infinite sum, this series here converges uniformly on any interval minus a comma a, where a is greater than 0, less than 1. And this is just one application. I mean, this is not the only this is not the only kind of set where this converges uniformly in any compact set. But this is the tie-in with what we saw before the break. So you know that compact sets are closed and bounded. And for instance, if you know that, I mean, of course you cannot expect this geometric series to converge at the endpoints. I mean, at 1, for instance, you get the sum of 1 from I equals 0 to infinity, so that's infinity, that's not convergent, clearly. So you can never expect actually this series here to converge uniformly inside this open interval. But if you take any smaller closed interval, so anything contained in minus 1 comma 1, any closed interval, like an interval of this form, it need not be of this form. Actually, it can be minus b comma a, where both b and a satisfy this condition. Then that will be a compact set, I mean, if you include the endpoints, and so the convergence there will be uniform. And why is this important? Because of the next theorem. If the sum from n equals 0 to infinity of an x to the n converges for all x in minus r comma r, then the differentiated series sum from n equals 1 up to infinity of n times a sub n x to the n minus 1 converges at each x in minus r comma r as well. And well, this is again this is sometimes called the differentiated series of the one above. So what can we conclude when we combine then this theorem with, the theorem with the previous one? You know that the derivatives converge at each x in minus r comma r. So the derivative of each one of these functions here, these are the fn's. And you know also that not only does this series converge for for a point inside this interval, but for every point in this interval. So in fact, you already know, you also know that, so it's actually not the previous theorem, the theorem before, the one before that you saw. So then we know that the series converges at least for 1 point, not only for 1 point, for every point in the open interval. So then the function is differentiable, and the infinite sum is differentiable, and the derivative is the sum of the derivatives. But more importantly, the sum of the fn converges uniformly to f of x. So as a corollary, as the sum of the an times x to the n, the series, sum of the ans times x to the n from n equals 0 to infinity, converges uniformly on compact subsets minus r, comma r. These are the main theorems you need to know. And in particular, this theorem tells you that you can differentiate term by term, power series, which is good to know now. So this function here is differentiable, and to obtain the derivative, I mean, if it converges for every point inside an open interval, then you can differentiate term by term. And I mean, so that this function is differentiable, and the derivative is equal to this series over here. This is adding all of the derivatives of these functions. These are the fn's here, fn of x, fn's of x. So this concludes this part. The next and last topic here will be integration. So Riemann integration, which will come next.